So hello everyone, my name is Carolina. So as Francisco said, I am a postdoc at Institute at IAG-USP at University of São Paulo. And currently I'm working with extratropical cyclones and extreme wave events. So I don't work with geochemistry at all, but I'm here today to talk about a contribution that I did for the work of Paula Santos. He was a postdoc at University of Campinas. And I was invited to this work to try to find a good model to model lithium isotopes. So this was a very good experience, and I'm very happy to share with you. And so then this work has had the contribution of many institutions. So first the University of Campinas, also from University of São Paulo, we have people from IAG, as well people from Geoscience Institute. And also we have people from University of Bremen in Germany working on this article that we produce with this model. So I would just tell you how we found a model to assess the chemical weathering flux with lithium isotopes. So let's see. First, I will give you some background about the team. The idea of this work comes from a thematic project funded by FAPESP, the São Paulo Research Foundation. And the goal of this work was to investigate the changes in the Earth system that lead to the appearance of complex organisms during the Ediacaran-Cambrian transition. That was more or less 542 million years ago. So inside this project, one important task was to investigate the cause of the onset of biomineralization, because this process that is basically the secretion of calcium carbonate by organisms was a very important innovation that just changed a lot how the ecosystem works. So this was a very important to the development of complex organisms. So what we know about it is that evidence shows that biomineralizing organisms first appear in very alkaline seas. So knowing that, what we want to know is what was the cause of this increase in alkalinity. So the main hypothesis that we have in literature is that this increase was caused by chemical weathering on the continent. But this hypothesis have not proven yet. So a good thing is that we can use lithium isotope to assess the continental weathering flux. So we can track it by using this type of isotopes. So what they did at first, so with some previous results about this work, they used carbonate rock samples from West Brazil to measure this lithium isotope and use it as a weathering evolution proxy. So here in the left side, we have the place where it was collected, the sample that is known as Corumbá Group, is part of Tamengo Formation. And here in the right side, you have the vertical section of the sample. So these dots over here are the delta 7 lithium measured by the rocks, measured from the rocks, sorry. And what we can see is that between the period that we are analyzing, we have two important decrease in delta 7 lithium occurring during this period. So what is this that means? Delta 7 lithium is basically the ratio between 7 lithium and 6 lithium. So a decrease in delta 7 lithium means that less 6 lithium is being retained in the continent. What it means that more 6 lithium is being delivered to the ocean. So it's why we have the decrease in delta 7 lithium. So these two decreases that we see here in the section is a strong evidence of the increase of continental weathering intensity. So based on these measurements, these previous results, we established two questions that we want to answer. The first one is, what is the weathering flux associated with the decrease of seawater delta 7 lithium values? And the second one is, what is the time necessary to drive the seawater from isotope value of 23 per mil to 15 per mil? That is one of these decrease cycles that we see over here. And only to clarify, we can in our case, we can call also the weathering flux as a riverine flux, because the most of the weathering that flux that brings things to the seawater comes from the river, so we can also use it riverine flux. So this question seems simple, but they are not easily addressed because we have a lot of uncertainty related to the time scale between the samples. And we also have lack of environmental parameters to build the model. So in this case, we just believe that the model would be an important tool to test the hypothesis, and at least to narrow down a little bit the wide range of possibilities that we had. So we designed a one-box model. It's a quite simple model, but as I said, we have a lack of information about the environment, so we don't have much parameters to feed the model. So it will not be useful to have a very complex model because we need to do a lot of assumptions, and maybe would not be good to have more uncertainty to our study. So we use a simple one-box model based on the mass balance equation. And when you're talking about isotopes, you can just use some analogous isotope balance equation, because you just will use a fraction term in each mass balance equation term. So here we have the evolution of the seawater reservoir, so partitioned by the seawater ratio, the evolution of this in time, and this is equal what comes in and what goes out. So it's a very simple X scheme. And for the lithium isotopes, the inputs that we have, the most important inputs that we have is the riverine, that is our weathering, and the hydrothermal input. And for the output, we have the autogenic clay mineral uptake, that is basically what goes to the sediment, and the oceanic crust alteration, that is some recycling that occurs near the seabed that may change the, that works like removal of lithium from the system. So when we open this equation, considering the inputs and outputs, we have this equation over here, and we consider, looking by the literature, that the output ratio, like the difference between the output ratios and the seawater ratios, remain constant. So is known as reverse weathering. So these two terms are constant. And one important thing to say is that you can see that we just took out the reservoir from the it will not change with time. We know that this is not 100% correct to do it, but we absolutely don't know how the reservoir will change with time. And then we deal with this in another way that I will show you in the next slide. But this the reservoir size will change according mainly with the riverine flux and the hydrothermal flux. So we just use another way to consider that change. So basically, we have in blue what we have as fixed value. We know them by literature, and we don't know the riverine and the ratio riverine flux parameters. We don't know that. We want to estimate it, and we know the change in the seawater ratio, but we don't know how much time takes to reach these values. So the fixed parameters we just got from literature, they are over here. So the scheme of the model can be summarized by this figure. We have in the inputs, we have the hydrothermal that we know, we have the outputs that we already know, and we have the change in the seawater that were measured, but we don't know how much time takes to do the shift. And we don't know much about the riverine flux. So it's one of the parameters that we want to find. So we don't have, the thing is that we don't have riverine flux and isotopic ratio available to the late Neoproterozoic. So we believe that to know how long would take the shift, we could establish some combinations of these parameters, but a unique combination of them would be a random task. So would just bring more uncertainty to our geological scenarios. So the way that we lead with that was to calculate not all the combinations, but a wide range of combinations that were capable to drive the seawater ratio from 23 to 15 per mil. So of course, we excluded from these some unrealistic values that we find. So we know from previous work that extreme riverine flux exist in the Earth's history, but we know that this was not the case of our of the late Ediacaran, so we just excluded these unrealistic fluxes. And knowing the fixed parameters, and knowing that we to do the simulation combining the riverine fluxes and ratios, we established 4 scenarios to deal with the problem about the reservoir being fixed in time. So in the first scenario, we just fixed N, that is the reservoir, and tau, that is the residence time. We fix them at the modern values. From the second to the fourth, we varied the, we changed the reservoir as a function of the, is over here, as a function of the residence time and the input fluxes. And we also changed between the second and the fourth the residence time, because we know that more intense input fluxes change the residence time. So we have a decrease of residence time when you have more strong input fluxes. So we changed these parameters to test our hypothesis. And so the solution of the model, we did some tests using the analytical solution of the equation, because you can find it. But we just prefer to use the finite difference solution using Euler method, because as we ran a lot of experiments in a lot of scenarios, it was very easier to implement it, and was very faster as well. So here are some results that we have. This figure over here showed the relation between the riverine flux and the time for the different simulations, for the different scenarios. And the color here show how was the simulation using different riverine ratios. So what we first can see that as the riverine flux increase, we have combined with a low riverine ratio, we have we achieve faster the target seawater ratio values. So because we are dealing with a decrease in the ratio, so when you have the riverine flux with lower ratios, you achieve the target value faster, combined with more strong riverine fluxes. And it is possible also to see that in the first one, it didn't adjust the reservoir according with the flux. And when you do that, we starting to have like a minimum time that things start to happen in the system. So we believe by these experiments that it's really important to adjust the reservoir according with the fluxes. And we also can see that considering then the second, third, and fourth experiment, we can find that exists a minimum flux and a minimum time that make that the system takes to reach the target value as well. So with these findings, we can say that a wide range of combinations of the riverine flux and ratio can reproduce the observed decrease of seawater ratio. However, only a minimum riverine flux of 24.5 10 to 9 allows this shift in all scenarios. So if you look to this value, is a really high value. So it's almost 2.5 higher than the present day's values that we have of riverine flux. So this indicates a significant weathering flux of lithium and other ions to the seawater reservoir. So with that, we believe that this is a possible cause of the increase of alkalinity of seawater. About the time required to reach the target value, if you think about this very strong riverine flux that we found, this might decrease significantly the lithium residence time in the ocean. So we just think that scenarios 1 and 2, where we consider the residence time at modern value, are not probable at all. So we just focus on scenario 3 and 4. And this scenario show that the shift required a minimum time interval around 1 million years and 250,000 years, respectively. So this for one cycle, and we need to remember that in our records we have 2 decrease cycles. So this was analysis for only one cycle. So the conclusions that we can take for it is the model used in this work supports the hypothesis that the high alkalinity environment that allowed complex carbonate-dependent organisms to develop in the late Ediacaran was promoted by the continental weathering increase. According to the experiments, it would be necessary a high riverine flux to obtain the lithium isotope rate shift observed in the records. And it's nice that also we can see that even a simple one-box model can provide valuable information regarding the geochemical environmental behavior. And it's not so easy to find works of this period, the late Ediacaran, and something more older than that. It's not easy to find modeling applied to these records. So it's nice that we can do it, and we can at least narrow down a little bit the probabilities that we have about the environmental change. And of course, to do it, we need to follow robust theoretical guidelines. But if you do so, it is possible to estimate possible scenarios attempting to reproduce observational records through modeling. So for the next steps, we are already doing that. We are testing this work hypothesis on a continental scale. So you need to know that for the late Ediacaran, when I say continental scale, we are talking about the West Gondwana continent. And so we're going to apply, again, the modeling, the lithium isotope model, to other marine sedimentary basin of same age, that in this case is the Bambuí group that is in the east central Brazil. So this is it. Thank you for your attention, and take care. If you want to contact me, you're free to do it.
Okay, thank you very much.